Hello, hello Nikita. Am I audible? Can you please tell me?
Yes, sir.
Okay. So I started discussing on the first question itself. So I'll tell it again. This is just very so just try to focus. Okay. So the question is, which is an example of adsorbate interaction. So I was talking about like what basically governs the ad layer pattern, and that is nothing but two kind of interaction, that is adsorbate and surface atom interaction and adsorbate atom interaction. Now what will be like the more predominating, that will actually govern the symmetry of the surface. Now we know symmetry of the surface, like symmetry of the ad layer. Now you know the symmetry of the surface because it is given like the Si silicon 100 or AU111, CU111, and that is already given in the question itself. So it is having actually four-fold symmetry. It is having actually six-fold symmetry and six-fold symmetry. So I was trying how it is six-fold or four-fold. That is already discussed in week one and week two as well. So now, if I can recollect how this surface looks like in like germanium or the sodium chloride on that particular surface, then if the surface symmetry and the Adler symmetry is somewhat similar, then we can say obviously this is there will be a very great part of surface. So that means that will be governed by add layer or add atom surface atom interaction. And if there is no role of surface, that times surface symmetry cannot be like implied into the Adler symmetry, and that time so practically add atom interaction is going to take place. Now, now we know everything. So if I can know the symmetry of the surfaces that are given. So this is germanium of silicon 100. We already know silicon 100 is practically a square type of shape, and this is having four-fold symmetry. Now, if you try to see, so each these small islands are practically kind of a square or rectangle. You can see. So the symmetry of the surface is somehow followed here. So that means it will have surface atoms and add atoms interaction mainly. But our question is asking about adsorbate interaction. Now come to the NaCl part. So we know AU111. It will practically have a hexagonal pattern, or you can say the FC111 looks somewhat like this in the three dimension. So it is actually having six-fold symmetry. But the add atom surface, just try to look at this. This add atom is a kind of having a square lattice. So my surface is hexagonal, or it is having actually six-fold. But my add atoms or add layer is practically having a square or rectangle. So that means four-fold. So that means there is no such role of surface. That means the surface symmetry is not trying to guide the or not able to guide the add atoms growth. So that means it is the add layer interaction. That means this is practically adsorbate interaction. Because we know also from the solid state idea that is uh, FC, that NaCl is a famous example of FCC lattice. So FCC is nothing but a like cubic, and if you think about the surface, it will obviously automatically be a square or a rectangle, like right. So I'm talking about NaCl surface. So once Cl atom is surrounded by the so all corners occupied sodium atoms and all. So that means this is purely guided by the sodium plus and chlorine minus, that are both are the add atoms interaction. So this will be the answer, because let's go back to the third option, that is cobalt on Cu111. So practically you can see this is a triangular shape. So this kind of triangle or this kind of triangle, but the triangular shape is nothing but the implementation of the surface, because the surface is 111. So practically the surface is always also having a six-fold symmetry, and this is, because this angle is, you can see this is 60 degree. So the adatom layer is also having a six-fold symmetry and the surface. So this is also guided by the surface adsorbent interaction. So whenever the surface symmetry is actually implemented in the adatom's layer symmetry, that time you can say that there is a surface and adatom's interaction that is mainly predominant. But if it is not, then that time it is mainly the adsorbent interaction. So I will a little bit talk about the adsorbed atom. So what are the interactions that are going to be there? Uh, so how can you how, like what will be the energetics? I'll come to that in some later slide. So now if we just look at that, so this is actually having fourfold symmetry, and the atom is also actually having square set. So this is not the the case, right? And this is also kind of having six-fold symmetry. So this is the answer, right? Is there any problem? So you get it, right? So I'll go back to the next question, right? So what is the question? This is written, which is an example of chemical vapor deposition. So this is kind of very informative kind of question. But before answering this question practically, if you just watch the lecture that from 10 to 15, you can easily answer this question, because this is very simple question. But I will try to discuss a very little thing about chemical vapor deposition. So what is chemical vapor deposition? So this is kind of a deposition, because before that we have seen the physical vapor deposition. Now we are going to get what is chemical vapor deposition. That means chemical vapor deposition means there will be some kind of chemical reaction that is happening, and with the help of that, the deposition on the surface is actually happening. So that means if there is a chemical reaction, obviously there will be chances of side reaction, and if there is chances of, like, side reactions are occurring, that means there will be chances of impurities as well. But then why we do that? Because these are practically kind of easy. If you don't thought about these two, these are practically easier than physical vapor deposition. But nowadays also we can get optimized procedure, and that's why chemical deposition is also important. Now, how practically chemical vapor diffusion actually happens? So we take the gaseous precursor. So whatever, uh, let's say let's say for the case silicon, we want to deposit silicon. So we need to have some precursor where the silicon is there. Precursor means some kind of molecule where is the silicon is there, and in the gaseous state. So that thing will be put there, and we need, that is something very important, that is carrier gas. Because I said about the chances of side reactions and impurities. So the carrier gas will actually carry the impurities or the side reaction products back, so that I can get a pure uh, deposition. But whatever I want to get, I will get that because of that carrier gas. Carrier gas will take back all these impurities, or you can say the side products, right? So these channels are for the gaseous precursor, and these channels are for the carrier gas. And then here it is going to the vacuum chamber where the surface is retained, and that is temperature control. So like giving the temperature, actually the reaction is happening, and whatever thing needs to be deposited, that are deposited, and the side products are mainly gases, which are actually coming back by the carrier gas, right? And that is collected as a form of liquid precursor. So this is the process. Now we have so there, that is given in this example of chemical vapor deposition. So you can see that is silicon and silicon nitride, indium phosphide. All these things has been discussed in the very first of the chemical vapor deposition starting. So I have given the slide. So how to get a polycrystalline silicon surface deposited in the surface? So we can take silane or trichlorosilane, and just increasing the temperature, one can deposit this silicon, right? One can deposit this silicon. So this is obviously with the help of some chemical reaction. So this is a example of chemical vapor diffusion. Now in case of silicon nitride, silicon, what is the chemical formula for silicon nitride? This is Si3N4, right? So obviously now, in case we need only silicon, now to get a silicon nitride deposition, we obviously get some precursor, one or two, where someone is having actually silicon and someone is having actually nitrogen. So we need both now because we need the surface with both the atoms. So that can be done using this process. So this is also again silane and ammonia. If we take and heat it, so we can get silicon nitride as a surface. And this, let's say, like just see this, in every case the side products are gaseous, which can be coming out, which can come out from as a help of the carrier gas, right? So this is also kind of deposition. Tungsten also, indium phosphide also, kind of help, like taking a help from some chemical reaction. Uh, Actually, we are getting the vapor deposition, nice vapor deposition of that. So what are the options? That is polycrystalline silicon. Obviously, that can be done. Silicon nitride, that can be done, and indium phosphide here, that can also be done. So this is the indium phosphide example practically. There is methane gas actually coming out, so that can also be done. And here also you can you just notice indium phosphide. So we need two kind of like we need a compound which is forming by two atoms. So obviously we need two precursor, one with indium, one with the phosphide, one with the phosphide. Yes. So that is the case. So what will be the answer? So all the options that are the example of chemical vapor diffusion. So obviously this is going to be my answer. Answer is also given in the like last part of the slide, right? You can see it there. So now go to the next question. That is question number 3. Which among the following, which among the following is true for Moray pattern? True for Moray pattern. So from the first lecture onwards and up to the last, like in this week, the lecture number 10 to 15, there's an extensive discussion about what is Moray pattern, how can it be seen. So that is the question that it is given here. So what is Moray pattern? So Moray pattern is nothing but if we have two similar kind of pattern, like similar kind of crystal lattice, let's say, with having a very small difference. Difference can be in angle, difference can be in the lattice parameter length. So then can optical illusion can optical illusion can be formed, and which can be seen as a pattern, and that is known, that is observed by the Moray, and that is known for the Moray pattern. So so let me first iterate the options. So what it is given? The spacing between two lattice is larger when angle between two lattice is smaller. We'll see what it is written here. We'll try to explain that. Now the second point is it forms due to lattice mismatch. So I said already, it can be a very small lattice mismatch also that can form a big lattice like that. That can form a new pattern in the crystal, in the surface, and that can be called, that is called actually Moray pattern. So that is obviously true, and I'll try to discuss that as well with the help of some mathematics or some help of some cartoons. Now, on increasing the angle between the lattices, the superlattices get smaller. So these two options are actually mainly related. So let's discuss this. Let's discuss this two at first. So then we can answer this. So this red one, and this blue one. So these are two same lattice. Just these two are having some kind of angle, and due to that, you just see there is some pattern that is observed, right? Some darker fringes and some lighter fringes, some darker fringes and some lighter fringes. So there is some pattern that is observed, which is not there in the both the lattice of red and blue. But due to that, two pattern are actually interacting somehow. A new kind of pattern is forming, and let's say this is the lattice parameter for the red one. Now the More pattern that is seen is having lattice parameter that is having the pattern, the super lattice, that is we are calling, is having pattern which is much larger than the normal pattern, normal parameters, right? So this angle between these two lattice, here it is given 5 degree. Now whenever we are increasing the angle, right, the pattern is again forming, but now you just see the repeatability of the pattern, or you can see the lattice parameter of that parameter. So this is forming. This is the lighter fringe. This is the darker. This is the lighter. So that means this is something forming. So now if I say this is D1 and let's say this is D2, so obviously you can see that D2 is much smaller than D1. Now, when we increase the angle much more, so that is, let's say this is 20 degree, so 5 degree to 10 degree to 20 degree whenever we increase. So just see, so there is the pattern is actually much more repetitive, or the lattice parameter is now decreasing very much. So let's say this is the D3. So what will be the relation? Obviously D3 will be much lesser than this. And if this is theta 1, theta 2 and theta 3, let's say, so obviously theta 1, theta 2, theta 3. So practically this angle is having somewhat reciprocal relation with the D. This D is nothing but superlattice parameter. Now why it is called, sorry, why it is called superlattice? Because the lattice parameter is actually increasing. So we can get the pattern in a some like a different distance which is actually increased than the previous one. So that's why it is called a bigger lattice, or it is like a super lattice. So we have seen that angle, whenever the angle between two similar lattice increases, that time super lattice parameter is actually decreasing. So let's go back to the question. So what it is written in the third point, on increasing the angle between the lattices, the super lattice gets smaller. So is it true? Now I can see this. So here the D3 is actually the smallest, and the angle for theta 3, that is actually the highest. So that is right. That is actually right. Yes, and so that means this option is also true, because what it is written, the spacing between two lattices is larger when angle between two lattices is smaller. So practically these 2 points are actually same point. Here it is written when the angle is higher, the lattice gets smaller, and it is written when the lattice is larger, obviously that time the angle is going to be smaller. So if it is true, that is obviously going to be true, right? Now we have talked about the angle, like the angular mismatch of the lattice. Now if it is just the parameter, so if both the lattice is having same kind of pattern or like same kind of grid like pattern, but just the pattern, just the lattice parameter of both the pattern are somehow like somehow not same. It is slightly different. So let's say the blue one. So this is for the blue one. The lattice parameter is D, and for the red one, the lattice parameter is D plus del D. So this is slightly different. Obviously, this is greater. So now, then also more pattern can form. How? Just see this line. So this line. So this line and blue. This blue and red line is exactly matching. If let's say like come to this, so just look from this. If you go right like that, so here only blue can be seen. That means blue and red is actually exactly matching, and again here blue and red is exactly matching, and in between the lattice is having some kind of shift because of the mismatch in the lattice parameter. So that means now the More pattern is actually forming, because after that again here you can see there is you can see there is no red can be seen, because it is actually overlapping with the blue. So if the lattice parameter is actually like we are observing some kind of pattern, just due to a slight mismatch in the lattice parameter, right? So this is nothing but the Moore pattern. So that means Moore pattern can form when two identical lattice have a different lattice parameter. So and this is the 2D, right? And there this is D. This D can be calculated from the exact lattice parameters or bulk lattice parameter of the two lattice, right? Which are formed in the Moore. So this is the equation. So this option, now come back to this option. It forms due to lattice mismatch. Obviously, this is also true. So that means the answer is absolutely all of the above because everything is true. It can form due to lattice mismatch. It can form due to angle mismatch. And whenever the angle is actually higher, that time lattice parameter is lower. So just try to remember this D, where D is the super lattice or Moore lattice parameter. Right? I think everything is clear. Okay. Now I want to give a basic like very everyday example of Moore pattern. So this is a photo taken by a camera of a man. You just see this heart, some kind of pattern is actually forming. This is also an example of Moore pattern. Why it is forming? Because Moore pattern can occur. Like this chart is actually having curtains in in some kind of pattern. Now this is so particular pattern, like these constant contents are repetitive detail. That camera obviously have a sensor resolution. It exists that camera cannot minutely resolve that, and due to that, the camera picture that we are observing is kind of having a slightly different kind of pattern than that. And due to that two pattern, which is actually having in the chart and that is forming due to the camera resolution problem, is going to interfere and create a more pattern, right? And that can be seen in various picture, right? This is an example. So you can clearly understand just by these two picture. So let's say this is a simple square grid, and this square grid you just slightly tilt that just by some angle. This is the same thing. Now if these two interfere or crosstalk with each other, some very different kind of complex kind of pattern can also form. So this is due to, let's say, camera resolution, and this is the actual pattern. So are different new kind of uh, pattern, that is Moore pattern, that can be observed. So that is a reason. So Moore pattern can be observed in various situations in day to day life, in various photos and all that can be seen. So Moore pattern is actually very very important. Now come to the next question. That is question number 4. What it is written? In which of the following cases the cobalt atoms at the interface have to undergo largest strain, right? Largest strain. So to answer this, we need to know the what is strain. It is already discussed in the lecture. The strain is practically the mismatch between the add layer lattice parameter and the surface lattice parameter divided by the surface lattice parameter. So practically the difference is actually causing the strain, because if, let's say, this is my surface atoms is having a1 space, and let's say this is my add atoms, if they are having same or similar a1, so that means there is no problem, there will be no strain. Like they will come and sit sit in the most favorable position and form the add layer, so there will be no strain. But if that is not the case, so let's say a different case, the lattice parameter is somehow like this, let's say A2. So obviously there will be a mismatch between which position they will choose, and depending upon that, and layer growth will occur. So like defining the strain in that add layer lattice, is very, very important. So how it is defined? This is the difference between the ad layer lattice parameter and surface lattice parameter divided by the surface lattice parameter. Now to answer this question, which one is having largest strain? What we need to know? We need to know both the lattice parameter, and because in every case the ad layer is same. Every case this ad layer which is going to be adsorbed is same. So that means if we know just the bulk surface parameter of each of this case, we can answer this. Which one will have the highest difference will go to the largest strain. So let's just sorry, here I am confused. So let me erase this part. So these are the lattice parameter, right? So these are the lattice parameter. So you can find it in the lecture as well. So I have taken these two from the lecture. And for this silver, I have taken it from a journal. I will give the reference here as well. So these are the lattice parameters. Now this is the lattice parameter for the add atoms, and this is going to be same. So now if we just measure the difference between ACU and ACO, AGU and ACO, AU and ACO. So you can clearly see these two are having the least. These two CU and CU are having least strain, and AG and CO are having highest strain, right? Because we are always like taking the minus from the surface lattice parameter. So, sorry, minus from the add layer lattice parameter, and that is always fixed in this case, right? So we have got everything. Let's say calculate it for strain for CU surface. So how what it will be? 2.51 minus 2.55, right? Divided by the surface, which will be nothing but 2.55, right? This is a reference for the AU. You cannot find this lattice parameter in the lectures. And this following this article, you can find it. So this will be my strain. So if you calculate, this will come around minus 1.5%. So you can see this is very, very less. And now if you calculate it for AG, so obviously it will be 2.51. Sorry, you can see there is a large difference, and it will come around just 13.5%, 13.15%, right there. So this is the highest. So obviously the answer is going to be this. So whenever the lattice parameter mismatch is highest, that time it is going to have the largest strain, and this strain practically determines the growth, how what kind of growth will happen in the surface. And I will discuss this whenever I will discuss about the growth, because depending on how the growth will be, there are some questions already set. So these are the strain that I already measured. Show you how to measure that. This is for the CO, and this is for the AGCO, and you can clearly see this is the highest. And AU will have similar kind of AG, but because of that, it is very slightly less. This is not going to have the highest. Like this is going to be the highest. So this is my answer, right? Okay. Now come to the fifth question. So, so Nikita, you understand this? Whatever I am trying to discuss, is there any problem? You can ask. Hello. Okay, I think we don't have any problem. So let's just continue our discussion. So let's come to the question number 5, right? So what it is saying, let's just read this. What happens at deposition of atoms on surfaces at higher temperature? So something temperature dependency is now coming. What happens at deposition of atoms on surfaces at higher temperatures? So we have already read about this in our 12th or in our base level. So there is something called KCP and this is TCP. So we know these two things, that is kinetics and thermodynamics, which determines how fast a reaction will be and the fate of a reaction. So depending upon that, normally if any system have an opportunity to go to two different product, so depending upon the temperature, depending upon the environment that is provided, it will decide the fate of the reaction, so which product it will be. And due to that, we can call this some product which is actually uh, which can be formed in the lower temperature. That means uh, to form that the activation energy is lower, so that's why it can form at the lower temperature, is called as KCP. And whenever the activation energy is very high, so that means in normal temperature or lower temperature cannot reach that activation energy. So whenever the temperature is higher, that time only TCP will occur. And that is what the uh, reaction coordinate energy diagram is telling you also. So the activation energy is lesser in this case, so this is the KCP, and the activation energy is higher in this case, this is the TCP, because ultimately the thermodynamic product is much more stable, but to reach that you need higher temperature. And KCP, the product is not that stable, but to reach that, low temperature is required because the activation energy is lower. So now if we again take the kinetic product and increase the temperature as well, so you can reach to thermal product that as well. So let me just take a very famous example that we have already read in class 2 or in the basic level. This example of famous example of 1,4 buta, right? So this is 1,4 butadiene. So now we are attacking. We are actually making an attack with HCl. So HCl is nothing but H plus. So H plus is actually protonating. So it can protonate here or here, because both way it will like reach with this product, with this carbocation. But this can actually resonate to this, and that due to that one can form this kind of a carbocation as well. And among these two carbocation, obviously this is 2 degree carbocation and this is 1 degree carbocation, right? So if we think about that, so this carbocation is much more stable. So the activation energy, because this is actually your transition state, so the activation energy as this is stable because of this 2 degree carbocation, right? Because we know the carbocation stability order is 3 degree, 2 degree, or 1 degree. So whenever it is more substituted, that time the activity is higher. In this case, one is 2 degree, one is 1 degree. That means obviously it is higher. So the activation energy will be lower because the intermediate is the transition state is much more stable in this case, and their activation energy I am writing as E act is higher, and their E act is somehow lower. But now from that, if we get the product, because what is that, which is nothing but adding this Cl minus, so we'll get this. And if we think about the product from this intermediate or this transition state, we'll get a product this. Now just think about these two products. This is this alkene. Now this is actually having alkene, which is not mono substituted because only one substitution. Now this alkene is actually di substituted. Now we know in case of alkene stability, monosub, disub, trisub, tetra, like due to hyperconjugation and all. So obviously, this disubstituted alkene is going to be more stable. So this product is much more stable. Then let's say this is A and this is my B. So B is more stable than A, obviously. So now if we try to draw the energy profile for this as well, let's say this is my substitute. One is going, sorry, one is going through smaller activation energy and one is going through larger activation energy. But this is the product stability is also higher in case of black, and product stability is lower in case of red. But the activation energy, you see, this is the activation energy for this, and this is the activation energy for this. So activation energy is lesser, and product stability is also lesser. So activation energy lesser means we can reach it in the lower temperature. So this is called KCP. And activation energy is higher. That means it cannot be reached in the lower temperature. It is we need higher temperature. That means this is TCP, and the product stability is higher. And so this is the case. Now keep these things in mind, and this is the reference of this that the photo I have taken. So you can go through the reference as well. So now keeping this thing in mind, we just try to solve this. What it is written. Kinetically controlled structure. What happens at deposition of atoms on surfaces at higher temperatures? This is point to be noted. This is higher temperature. So we know in higher temperature that higher activation can be reached, and if higher activation can be reached, the product will always be the stabler one. So we will get obviously thermodynamically favorable structure, right? So these 2 points are as it is cancelled. Now between these two, thermodynamically favorable structure because relaxation of atom at the interface requires a lower barrier. Barrier means nothing but the activation energy. So what is this written? Because relaxation of atom at the interface requires a lower barrier or a higher barrier. So now again come back. So don't need to come back even. For TCP, what is activation energy? This is higher. So that's why it is actually happening in the higher temperature. So what will be your answer? Relaxation of atom at the interface requires higher barrier. Right? So this is your answer. Right? I don't think any problem is there. Okay. Let's go back to the question number 6. So this is totally question is given from the lecture number 15, and I'll discuss a very few I'll discuss my bit, but I will encourage if you have not seen this video of the lecture 15, please watch it because this is a very beautiful discussion on the similar thing whatever discussed about KCP versus TCP, and this is a beautiful example that is occurring on the surface, and that is about everything is about KCP versus TCP. Now this is 180 Kelvin. Just go one by one. What happens when CO film is prepared on Ag11 surface at 180 Kelvin? Okay, so 180 Kelvin means we all know. So this is much lower, much lower temperature than room temperature, right? So this is very low temperature. So at this low temperature, we already know at this low temperature, TCP cannot form, right? Obviously, a KCP will form. From the previous discussion, we can say that. So this point, add layer has kinetically controlled structure is very true, right? Okay, let me join. Hello, please find. So obviously at low temperature it is going to be kinetically controlled. And what it is there? So this is the two thing. One is at 180 Kelvin and one is at 300 Kelvin. So obviously 180 Kelvin is going to be the KCP, that is kinetically controlled product. And just see, this is actually having 6.5 degree rotation, because this white thing, these are the surface lattice vector. And if you see about this one, this is your add layer, and this is your surface layer. So these are looking kind of similar because the angle is very very small, 6.5, but these are not, because it is actually measured by this something, and this is 6.5 degree it is having actually lattice parameter. Lattice vectors are actually rotated by 6.5. So obviously we have seen in case of Moore pattern, depending upon the angle, we can get the Moore pattern, and if the angle is higher, the super lattice parameter will be smaller and all. Right? We know everything from the discussion. Now it is given 22.5, and we know this is actually having this is actually having 17.3, and this is actually having 22.5 on the discussion. So, and just try to comprehend that this is actually having 6.5 degree and this is actually having 0 degree. So obviously, whenever the angle is some angle is there, some angle is there. Because 0 is not. We cannot say that like angle is like in case of 5 degree to 10 degree. If we increase, the superlattice parameter will be decreased, right? So obviously, this will have this will have higher distance, higher superlattice parameter than this. And we know in case of 180 degree, this is 22.5 and this is 17.3, because there is no such kind of uh, angle resisted things are seen. Also, just see C1 AG lattices are tilted with respect to each other. Obviously, you already know it is tilted with respect to each other by 6.5 degree. So all these things, their main point is it kinetically controlled or the thermally controlled, that we already know from the uh, previous discussion of this TCP and KCP, right? So this all the 3 points are going to be true. So the answer is going to be all of the above, right? Okay. So let me come to the question number 7. So which of the following growth is Frank Dar Marve growth, that is layer by layer? So before discussing that, these are the photos I have taken from the lecture videos only. So these are the options and these are the photos images. We'll discuss this, but before discussing this, we need to know what is Frank Der Merve, or whatever the things can be done. So there are three type of ad layer growth is seen. One is Frank der Merwe, or it is called layer by layer, and another one is Volmar Weber, and another one is Stransky Kostanov. Right. So this theta is actually the coverage. So when the coverage is very very low, less than 1 mm, that time all growths are kind of similar, because obviously there is no options. That's why all kind of groups are similar. Now when we increase the coverage, so now it can like grow above that, or it can feel that, right? So it can grow on top of that, or it can like fulfill one surface altogether and then go back to the other one on top of that. So if these islands are actually like again adsorbed by the same similar molecule, and one can form this kind of structure. So there is like whenever it is there with the low coverage, however the shape was, it is actually growth having growth in the z direction, you can say, or the height is actually increasing. Now if it is not only in the z direction, it is in the xy plane, like the layer total layer is actually forming first, and then above that some kind of island is forming, and again that layer is after you increase the coverage, that layer is totally completing, now from this to this one layer completed and some kind of island form. And when we increase the coverage, Again, the second layer formed. This one is one, this one is two, and this was three. The second layer is formed. Now three is actually formed here and there. So again, if you increase, it will go like the third layer will be covered, and then some fourth layer will be observed. So this is actually going layer by layer, right? Layer by layer. It is also written here. And whenever this layer by layer is observed, that is called as Frank der Merwe uh, growth pattern. And now, just see this. This is exactly opposite of the layer by layer. So whatever the coverage was, when the coverage was very less, that time obviously some kind of islands will form automatically. Now, if we increase the coverage, in the previous case, the layer is actually forming, then it is island, like then on top of that some kind of layer is forming. Now here, the these spaces are not covered. The spaces are not covered. Rather, there is a growth in the z direction. And whatever it is formed, only above that some kind of growth is observed. So that means that is not layer. The total layer is not forming. That is a island kind of formation. One island is actually having growth in the single direction, that is in the height or jet. So that kind of growth is called as Weber growth or island formation kind of growth. And there is also a third kind, which is a very balanced between both layer by layer and island. So some layer at first form, and then after that some kind of growth is only formed. Like only first layer has been formed here. And second layer onwards, there is only island growth has been observed. So because you can see directly by the first discussion what we have started with. So to go, like get any kind of add layer on a surface, we need to consider two kind of force. One is add a layer, add layer interaction. One is surface add layer. So these two kind of interaction is always present. Whenever, let's say this is my surface, and let's say some kind of foreign atom is coming. So obviously this is going to react with the surface. So there will be a surface atom interaction, and after some point, obviously these two are going to cross talk each other. So that is also adsorbate interaction. Now, when a surface is actually totally forming, and then some layer above it is forming, and then that layer is completing, and then above it. So obviously, that is due to surface and add layer. So because the surface and add layer are interacting so much, so that all the places are actually adsorbed, and after that, a second layer is absorbed, and surface interaction is so much, so that second layer onwards, again the same thing is happening. Now, if adsorbate interaction is very much higher than the surface, in this case, this is the case. If this is happening, adsorbate interaction is much higher than the surface adsorbate. So obviously, after a certain thing, only adsorbate will on the second layer of add molecule will adsorb on the first layer of the add molecule, because this interaction is higher. So there will be this kind of growth, obviously, because the surface adsorbent interaction is not that much. But in case of Stansky-Castanov, that time surface adsorbent and adsorbent is kind of similar. Now, whenever you move in this direction, let's say this is z direction, so the influence of the surface is going to decrease, right? Influence of the surface is going to decrease. So that's why, obviously, in this region, added, because surface is much far than the adsorbent layer, so added interaction will increase than the surface area. So that's why after a certain layer, there will be island kind of formation. So this is both island and the layer by layer, and that is called as Stansky-Castanov. Now try to answer this. So uh, obviously surface interaction will follow whenever there will be very less mismatch with the two, because if there is mismatch, so there is obviously surface and adsorbent interaction will be there, but due to the mismatch itself, one cannot, because the lattice parameters, if the lattice parameter of the surface atom and the air atoms are very different, then if the interaction is let's say case the interaction is much higher, but still it cannot be formed by a layer, performed as a layer because of the large stain. So in case of that Van der Merwe, uh, along with that surface adsorbent interaction, we need to think about that there the strain is less in that case. Okay. So, like before going to the answer the question itself, let me give you a hint about some two three things as well. So, as I said, this is add atom interaction, and this is surface with add atom interaction. So, this add atom interaction, and this will follow this kind of a curve, and this is the lowest point. So, where the repulsion will be, so where is there will be the highest interaction energy, and because this is happening between two add atoms, it is called as a delta E intra, and this is between the two kind of add atoms and substrate. So, this is called del E inter. Right now, in case of layer by layer growth, obviously low strain is required, as I discussed already, and this adsorbed surface interaction needs to be stronger. Otherwise, island kind of formation will be there. Now, if there is a misfit at the interface, so obviously it cannot be by layer, and that time island kind of growth is much favorable, and that time also adsorbed interaction are stronger. So in case of Van Weber, so this will be the case, and this will have this FM growth or layer by layer growth, this will be the case, right? So now now try to discuss it. We already seen in case of CO on CU, the strain is very small. Strain is very small. And in case of NaCl AU, we also seen this is an example of add atom interaction, high add atom interaction. So add atom interaction, if it is high, that cannot be a layer by layer growth. And if in this case CO on Ag111, we already measure the strain that come around 13.5 or 15. So the strain is much higher, right? So this cannot be the case because this is adatom. So this cannot be the case because of the strain. And here you can see, so these are different kind of colors coded because already island kind of growth is forming, because that silicon itself is having sorry, germanium is actually having a similar kind of interaction between them. So this is actually like a big layer also formed and island also formed. So this is kind of not only the layer by layer, because of by looking at the picture itself you can see. So what will be the answer? So this will be your answer. Copper, because there's very less strain. Strain is minimum, and also the surface is actually guiding. You can see the symmetry of the surface, and this is sixfold. The symmetry of the surface is actually guiding the geometry of the add layer. So obviously, the add atom interaction is not that much. Rather, the surface and add atom interaction is higher. So this is going to be my answer. Hope you understand this. Okay. Now come to the Bonner-Weber growth. We already discussed about the island growth. So just read this point and you will understand what will be the answer. Large strain or the misfit of the at the interface. Obviously, it is required. Otherwise, a layer by layer growth is possible. Adsorbed atoms are obviously needs to be stronger. That's why above one another atom layer will happen, because that is the island growth, right? So this is again true. Now, intra. What do you have told about intra? Intra is nothing but add atom, and inter is nothing but surface and add atom. So, intra needs to be higher because to grow the island, So this is also true. So this is my answer, all of that. Right? I hope you understand this. Okay, come back to the 9. In which of the growth mode there is a balance between the adsorbed surface interaction and the adsorbed interaction? So obviously we know this is nothing but layer by layer, because the first question we discussed, and this is the island. And in case of balance, that is named as Stransky-Krasnov growth. And let's see this as well. This is layer plus island both. Right? So this is my answer. And that is the pattern how you can form. So this is the first is layer, and then this is island kind of thing. Right? And this is a very very good question. How amorphous layers are formed? You can get it in the lecture itself as well. So whenever, so we have seen about everything. Like we have seen about like surface atom interaction needs to be higher some case, and at that case, strain is minimum. Add atom is higher. Strain is there. Strain is there, and add atom is higher. So this is my FM. This is my what it is called, VW. So, and when there's a balance, that is Stansky Gastanon. Now, if let's just think about a situation when strain is higher, also very large misfit, because these two are same point, and also atom interaction, surface adsorbed interaction is much higher, because when surface adsorbed interaction is higher, that time normally FM growth can be observed, but that time strain needs to be less. But if the strain is also higher and surface adsorbed interaction is also higher, how what it will happen? So in the if it is a surface, there will be like this kind of thing, only very less growth, and that is nothing but the amorphous layers. So this is large 10 high affinity of adsorbed atoms, surface atoms, and that is called. So what will be my answer? This one, right? So these are the questions that needs to be addressed. So I hope I have understood this thing, right? So let me uh, like finish it here, and we'll meet again in the next week, right? Thank you everyone for your kind attention. And obviously you can see these lectures by providing the link will be provided by the NPTEL team, and also you can go to the go to the YouTube channel, Tanmay Khan PMRF IIT Kanpur, and there will be a specific playlist created in surface and interfaces in NPTEL, and there you can find all the videos, right? So thank you again. So that's